Hello, I am Frederic Bless and I will be your host today. Gianfranco Guidati studied at the University of Stuttgart, where he did his master's and PhD degrees. He then worked for Alstom and then for GE, before landing to ETHZ in Zurich in 2017, thanks to the SCR program. And since last year, he works at the Energy Science Center at ETH. He's also the manager of the suite DeCarbch program. Gianfranco, you say that you see technologies as Lego bricks that need to be combined in a smart way to create a functioning system. And the suite DeCarbch program was created to improve the ways to join them together. And today you are presenting a very important set of Lego bricks, if I can say, which are crucial to enable Switzerland to be net zero by 2050. And they are negative emission technologies. Gianfranco, the floor is yours.
Thank you, Fred, and hello to everybody. It's a great pleasure to talk about this subject. And actually, as you all know, DeCarbch is decarbonization of heating and cooling in Switzerland. It's a lot about thermal grids, about industrial heat, about storage, and so on. And but there's also negative emission technologies. And I hope I can explain in the next 25 to 30 minutes why this is an important subject also for our project. So let me dive right into by asking the question, why do we need negative emissions? When I speak to people about carbon capture and storage and so on, I sometimes get a strange look like, okay, but we do electromobility, we do heat pumps, we do a lot of photovoltaics. Do we really need this also? And I fear, yes, we will need it. I stole this very nice graph from BAFU, from presentation from BAFU, and you can see that there will be some residual emissions after we have done everything we possibly can, like electromobility and all the things I mentioned. There will be still emissions from industry, cement plants, and so on, and there will be especially also emissions from agriculture. And to compensate this, we need to do two things, as BAFU here puts it very nicely. One is what they call CO2 avoidance. So we need to capture the CO2 at the source, for instance, from a cement plant, and put the CO2 underground, CO2 capture and storage, CCS. But we also need to remove CO2 from the atmosphere. These are the famous negative emission technologies that I will talk about. And this is especially for sources which we cannot possibly do something about, like in agriculture, for instance. Now, in the scenarios that BAFU and BFE have put forward, we have some 2 megatons of negative emission technologies in Switzerland, especially bioenergy, CCS. I will explain this in a minute what it means, and 5 megatons abroad with direct air capture. That's one possibility. And but I want to put the stakes a little bit higher. So I use the same visual here and repeated essentially what you've seen before, with a small change that I want to know, I want to understand whether we can do those 7 megatons of negative emission technologies actually in Switzerland. So 7 megatons of CO2 per year removed from the atmosphere here in Switzerland. But actually, we can also make it a bit more ambitious even. At the moment, we are not talking about aviation yet, but we have to, we should, and it's actually starting now, the discussion, including aviation. And this may be some 6 megatons which come on top of this on the emission side, which will of course tip our balance, which needs to be compensated then with even more negative emission technologies. And this is the space I want to explore now. What technologies do we need for that? And is there the potential to really do this? What I will use for that is energy system modeling, as usual, when I talk about those things. And what is important for this to understand is that the basic thinking, the basic tool is really to understand CO2 streams. There's 2 main reservoirs, let's say, of CO2. And actually, strictly speaking, it's not CO2, but it's a fossil fuel, for instance, or also a biological fuel like a biomass, which, however, contains CO2 in the sense that if I burn it, it will be released as CO2. So we have those 2 reservoirs. One is the subsurface, from which we can extract fossil resources. And the other is the atmosphere, from which plants, obviously, extract CO2 and make this available to us in the form of biomass. We can also do direct air capture, obviously, and I will talk about this as well. Now, this undergoes normally then some kind of process. often a combustion process, but it could also be a gasification or pyrolysis process, possibly using also CO2 separation. And as a consequence of this, we again have two CO2, now it's really two CO2 streams. One may go to the atmosphere back, that's released to the atmosphere, and the other may go to permanent storage in the subsurface, or in the case of the famous biochar, also in the soil. Yeah. So it's these balances that we need to understand in order to appreciate the value of negative emission technologies. And what I'm really interested in is two quantities. One is what I call the atmospheric balance. So do we emit actually more than we take from the atmosphere? Then we would have positive CO2 emissions. Or do we emit less than we take from the atmosphere? Then we would have negative emissions. That's what we're interested in. And the second quantity I'm interested in is the amount of permanent storage, the amount of permanently stored CO2 in the subsurface, because this is coming with a challenge. We need to transport it somewhere and we need to store it somewhere. So it's these two quantities that I'm really interested in. Yeah? So let's have a look at certain technological elements and how they fit into this scheme here. Let's start with something that obviously we do today and we will have to stop doing in the future. That is fossil heating and mobility. We obviously extract fossil resources in the form of oil and gas from the subsurface. The process is the combustion, internal combustion engines or in gas or oil boilers, and we release it to the atmosphere. Clearly, it's a positive CO2 emission, which, there's not a lot we can do about it. In the moment that the emission is generated, it will go to the atmosphere. The next option is gas CHP plants with CCS. Again, we will extract a fossil resource from the underground. This goes into a processing, in this case, let's say a gas CHP plant, possibly with CCS. And as a consequence of this, we have a big CO2 stream that goes permanently to the subsurface, and a small one because normally we cannot take everything out of the flue gas of a gas turbine. This still goes to the atmosphere. So basically, we are neutral. We are CO2 neutral. Another option to be CO2 neutral is, of course, let's say a wood pellet boiler, an alternative to oil heating, as we may use it today still. CO2 is extracted from the atmosphere with biomass growth. And when we burn it in our wood boiler, it is released back to the atmosphere. And this is CO2 neutral again. We can do, this is nice because we are CO2 neutral, but we can do better than that. If we would use a wood CHP plant together with CCS, we would have biomass growth, yes, and we would have a bigger unit, a wood CHP plant, which is probably connected to some district heating network, and we can apply CCS. What then happens is that the CO2 is taken from the atmosphere, and the largest part of it goes permanently to the subsurface. Again, a small part is released to the atmosphere. And with this, we are generating definitely negative CO2 emissions. The next option I want to look at is an interesting one, because this is waste-to-energy plants or cement plants with CCS. They're a bit more complicated. Waste-to-energy plants, they burn partially fossil waste and biogenic waste. And cement plants, they may use wood to generate the heat, but there's definitely the limestone that enters and the reaction that takes place releases fossil CO2. So we have, let's say, two streams one coming from the atmosphere, the other coming from the subsurface. And there's a process. And again, when we separate the CO2 and bring it underground, we can generate negative emissions because we release less and we take from the atmosphere. It's a little bit less negative, let's say, than the wood CHP plant you had seen before. Now, I mentioned briefly pyrolysis. Pyrolysis is a technology where you don't burn biomass, for instance, but you heat it up under absence of oxygen. And what then happens is that volatiles are released. These can be burned to generate heat for the process. And what comes out in the end is a certain amount of CO2 that is released to the atmosphere, and the rest leaves the system as carbon. And this carbon is so stable that it can be put in the soil. It enhances the soil, or there are also ideas to add it to concrete. So also this generates negative emissions, a little bit less than the wood CHP plant that I mentioned. And then finally, obviously, we have the famous direct air capture. This is technology that is being developed by the Swiss company Climeworks, where we extract CO2 from the atmosphere, which is much more difficult because there's a much lower concentration of CO2 in the atmosphere, and we bring it permanently underground. And of course, we generate negative emissions. Now, this all what I showed you so far sounds awfully qualitative. So can we put some numbers to this? Can we make this quantitative? Yes, of course we can. And what we need for this is energy system models. And the energy system model, it balances all the CO2 and energy streams within the energy system, which is heating, electricity generation, and mobility. And the results I'm showing were generated with Swiss Energy Scope, a model that was originally developed at EPFL, and then further developed at ETH. There's a linear optimizer that optimizes the design of the energy system and also the operation throughout the target year. And I'm jumping actually in 2050 and want to understand how does the world look like in 2050. We minimize total system costs for a given CO2 target. And then we vary actually the CO2 target because we want to see which technologies are actually important for which CO2 targets. And this is the way I will also present my results in the next minutes. So let's go back to these various technologies that I was talking about before. Let's start again with the fossil heating in mobility. And what I want to understand is how do these emissions change if I change the CO2 target from a not very ambitious target of, let's say, plus 20 megatons per year for the whole energy system down to a very negative range of up to minus 16. So I need two graphs for that to show you this. And the two graphs are actually showing what I announced before, the atmospheric balance. So how much do we actually emit net to the atmosphere, and the amount of permanent storage. So these are two graphs which you will keep on seeing actually in the next couple of minutes for the various technologies. Okay? So the unit is always megatons per year, megatons CO2 per year. And here on the x-axis, you have the annual CO2 emissions of the whole energy system. That's the overall energy system, not just the specific technology I'm looking at. And important is to understand a few points on this x-axis here. If we want to be net zero, not counting aviation, we have to be in this range here. -6, -5, maybe something like that. So we need to extract actually CO2 from the atmosphere to compensate emissions, especially from agriculture. If we would even consider aviation, if we want to compensate aviation, we have to go even more negative. So we have to be at maybe -12 or something like that. So now we use the energy system model to we decide I want to have the optimum system now for 20 megatons CO2 emissions per year. I run one scenario for the first CO2 target and I get a point. Doesn't look very spectacular. So we will have these kind of emissions from fossil heating and mobility, so almost 10 megatons. And of course, there's no permanent storage because in this case, it doesn't apply. Now, one point is not interesting. What we do always is we do a Monte Carlo variation. We do a Monte Carlo variation of all parameters that we consider uncertain, which would be population count, the climate in the future, prices, and so on and so on. So in reality, we have a distribution. I don't believe in single numbers. I would like to show a distribution. And now this is done now for 20 megatons, and then we repeat it for 19, 18, and so on, and we get a complete picture. We repeat this for every CO2 target, and we see the trend. And the trend is very clear here. When you're not very ambitious in your CO2 target, you're still emit 20 megatons in the energy system. Fine, continue burning oil and gas and gasoline and diesel in our vehicles. But there's a point where this has to go down, and eventually you stop using it. That's more or less the only option we have here. Now let's look at the next one. This is a large gas plant, a gas turbine power plant with CCS, or maybe a small CHP without CCS. And it actually looks very similar to what you saw before. At the beginning, when we're not very ambitious, yes, let's use this. Okay? But then there is actually some CCS that is being applied on big gas power plants that are not connected to heating networks in this case here. But then in the long run, the best thing is to just stop doing it. Okay? So to avoid those emissions by simply not using this technology anymore. Actually, gas power plants are still part of waste to energy plants. You will see this in a second. The next case is a cement plant. In a cement plant, we have the extraction of limestone from the subsurface, and we have biogenic waste that is being burned. We have the I'm sorry. This is not completely correct here. This should be a cement plant. Then we separate the CO2. We bring most of it underground, and a little bit goes to the atmosphere. That's the option. And what you can see here is, again, the atmospheric balance. So today, or let's say when we are at still 20 megatons per year, or those cement plants, they emit the usual 2 to 3 megatons per year, what they also emit today. But actually, they could turn into, from net emitters, they could turn into net sinks. And actually, you do this by switching to a biogenic fuel for the reaction, and by also using a wood CHP plant to provide the heat for the CO2 separation process. So with this, a cement plant can actually turn from a net emitter to a net sink. The same is interesting. The same can be done for waste to energy plants. Here we have the biogenic waste, and we have the fossil waste. It undergoes, again, combustion. If we separate the CO2, we can bring it underground. We can generate negative emissions. And actually, it's even a bit stronger than what you saw before for the cement plant. So again, a waste to energy plant can turn from a net emitter to a net sink. This is a bit a special waste to energy plant that we are thinking of here, because this is adding also a gas turbine, and it's also adding a wood CHP plant. This is let's say, it's a kind of archetype which we modeled following a bit the Bernd Forsthaus plant, the waste to energy plant, which they have in Bern, which is also a combination of a waste to energy plant, a wood plant, and a gas plant. So a waste to energy plant can actually turn into net sinks in the future. Let's have a look at pyrolysis. Pyrolysis can have a certain share in reducing CO2 emissions, but it's a bit less than the others. The thing is that you don't necessarily want to use wood for the pyrolysis, because wood is such a valuable resource that you can use for all kinds of things here. So what I assume here, that you are mainly using digestate, maybe from manure, anaerobic digestion, and there is some potential, but it's not that huge. The last thing I want to show is the direct air capture. The direct air capture is, of course, very interesting, because we extract directly from the atmosphere, and more or less 100% of the CO2 that we have extracted can then go underground. And the atmospheric balance, of course, is well, we don't do it at the beginning, but then in the end, we can generate a lot of negative emissions with direct air capture. So these were the various technological options, how to either avoid emissions by just not doing something that we are doing today, like not driving around with diesel and gasoline cars, not burning oil and gas in our houses, and then let's say capturing CO2 from point sources up to the end, where we would capture CO2 directly from the atmosphere. So let's put these things together into one graph, and that is shown here. These are the various CO2 storage options all put together. On the left, you can see the CO2 separation from the point sources, the direct air capture, and then the carbon storage in soil or concrete via pyrolysis. And you can see again, and that's important to say, when you don't have a very ambitious CO2 target, you're not starting with CCS. You're not starting with CCS from point sources, and also you're not starting with direct air capture. You do all the other things first. You decarbonize heating and mobility with heat pumps and with electric cars. But then comes a point where you start deploying CCS on point sources from a certain ambition level on, and then later comes a point where you even deploy direct air capture. And just want to remind you again, it also depends a bit on the target that we set ourselves. So if we set, for instance, a net zero, not counting aviation, we will definitely need those separation from the point sources, but we don't necessarily need direct air capture. If we are more ambitious and we say, no, we want to also compensate emissions from aviation, we need everything. We need the decarbonization via electromobility, we need the point sources, and we need even direct air capture here. So this was an overview of the various negative emission technologies and how they play together to really reach our CO2 targets. Now, let me close by raising a few questions that needs to be addressed, and that's basically the work that we are going to do then also in DeCarbch. And the first one is the optimum heat integration of the CO2 capture process. I didn't talk a lot about the CO2 capture process. So essentially, what this is there's an absorber where the flue gas of a combustion plant is going through, and it leaves then in the form of cleaned flue gas. The CO2 is absorbed by a solvent, it's normally some kind of amine, and then you have a stripper where you remove the CO2 again from the solvent, and you have more or less pure CO2. The problem is that the CO2 separation has a pretty large heat demand at a relatively high temperature, maybe 150 to 180 degrees. This is especially here in the stripper where you have to add this. But it has also a cooling demand. And that's the interesting thing. The cooling demand is obviously at a lower temperature than the heating demand, but it's still at a temperature that could be interesting. It could be interesting for energy grids. It could be elevated a little bit by a heat pump and then maybe used directly. And this is an opportunity. It's a challenge, but it's an opportunity also to be explored via process integration, pinch analysis. And this is, for me, the direct, obvious touching point to the rest of DeCarbch. We'll work with Beat Wellich and his team on this within the work package 12 of DeCarbch. But generally, if we come with a statement that, hey, we have a lot of energy, where can we use it in thermal grids and so on, I think this is interesting for DeCarbch as a whole. So that's one important question to be addressed. Another question, which we will not really address in DeCarbch, but it's so important that I still mention it, is the question where to store the CO2. Before the times of sweet DeCarbch, I was working for the SCCR supply of electricity, and there we looked already at CCS in Switzerland. Already before that time, there was a first study already more than 10 years ago, where the potential was estimated to be relatively high. Several decades we could store CO2 in Switzerland under the Mittelland. You can recognize here the Mittelland. Unfortunately, as researchers do, we had a second look, so we wanted to know it better, and the potential went down. It went down from a few decades to probably only a few years, which means that we shouldn't really bet completely on underground CO2 storage to be possible in Switzerland. We need very likely a European solution. So we need to connect to a network, which obviously doesn't exist yet, and to storage sites in the Northern Sea. And those storage sites, they exist already because the Norwegians for many, many years already pump CO2 underground in depleted oil and gas fields. That is technically possible. The difficulty is to bring it there. And what was studied just recently in a study funded by Swiss Federal Office of Energy is how to get the CO2 to the Swiss border. And so there was a first layout that had been made, which connects actually the cement plants and the waste to energy plants via a western trunk line and an eastern trunk line. You can find all the plants here on this map, and it brings them to Basel. And from Basel north, hopefully, we can arrange with our neighbors, so with the Germans and with the Dutch, to have a pipeline that brings us to Rotterdam, from where it could be picked up by companies like Northern Lights, which will store then the CO2 underground. The alternative would be to go south via Martigny to Geneva and to go to the Mediterranean Sea. If you're interested in this, there's a very interesting project at ETH now, the Demo Abkama project, which will look actually at the implications of the CO2 transport and storage. There are a couple of further questions which we need to be addressed. I talked a little bit about aviation. I really say a little bit because this was not really the major subject of the work that led to this presentation here so far. So far, we have only considered the compensation of fossil fuels. So we assume we still burn fossil kerosene and we want to compensate it. And we see which technologies are needed to come there. The synthesis of fuels via power to liquid or biomass to liquid may offer additional opportunities which need to be explored. And this will be one of the next steps in this scenario analysis. It's not only opportunities, also challenges, because consider that if you want to have a synthetic kerosene, it will contain carbon. And this carbon cannot be put underground anymore. So it may actually jeopardize our possibilities to do negative emissions. This all has to be put together in one understanding of those CO2 streams that I was talking about in the last minutes. Pyrolysis, it's a big hype at the moment. It's considered in the model, but it has to be further worked out. The question is also how realistic is it to pyrolyze digestate from manure fermentation? There's a problem with logistics, and there's definitely also a problem with nutrients, which need to be considered properly. And then carbon storage in wood buildings. It's also a subject that is very hot at the moment. I need to put this in my model. I prepared it already. And the interesting thing will then be to understand the trade-off. So we have a wood building versus a concrete building. Fine, but the concrete building is not a steady target. It gets better because we're actually capturing CO2 possibly from cement plants. And with the wood, we could do something else. We could burn it and put it underground and generate negative emissions. So this will be very interesting in one of the next steps to understand really this balance. What does really make sense? So let me conclude by summarizing again the steps towards net zero. And let me pick up what I said at the very beginning. This is not about doing CCS in order to be able to still continue driving around with my diesel SUV. No, you have to get rid of the diesel SUV and you have to get rid of your oil and gas heating. And then you do also CCS in order to compensate emissions from waste plants, from cement plants and so on, where you can do nothing about it. And then in addition to that, you need even to generate negative emissions, to extract CO2 from the atmosphere with negative emissions technologies. Bioenergy CCS, you've seen different variants of this, wood CHP plants, but also cement and waste to energy plants, and eventually also direct air capture. But whether we need this technology in Switzerland depends on the ambition level that we have for our emissions in the future. This was the short overview I wanted to give you. Thank you very much for your interest, and I'm looking forward to your questions.
Thank you very much, Gianfranco, for the very, very interesting presentation.